LESENSE stands for Low Energy Sensor Interface. It is in essence an ultra-low power peripheral that can autonomously monitor and evaluate analog sensor events. In this training module, you will learn the basics of how LESENSE operate in deep sleep mode, sensing both capacitive, inductive or resistive sensors. To understand how LESENSE can save energy, let us first look at how analog sensor measurements are usually done in a generic MCU. This analog event graph represents some external analog event that we want to trigger on and measure. It can either be a change in capacitance, like capacitive touch, or it can be inductive events like metal detectors. It can also be something as simple as the analog output of a resistive light sensor. A generic MCU would typically need to use the CPU to evaluate the sensor at some specific scan frequency. When it detects a change in the analog value, it can do some processing before it continues with the sensing. The red graph shows relative energy consumption in active and sleep mode of the CPU. With an EFM32 MCU, the LESENSE module can autonomously do the sensor evaluation in deep sleep mode. Running on the low frequency oscillator, it can autonomously duty cycle other peripherals that is needed for the sensor measurement, letting the CPU sleep until a threshold is reached, for example when a finger touches a capacitive touch button. With the built-in low-power Statemachine, LESENSE can also evaluate several events before it issues an interrupt to the CPU. It can do quadrature decoding, simple communication packet decoding, or it can count events and only wake up after a certain number of events has occurred. The Low Energy Sensor Interface offers autonomous sensor measurements and evaluation in deep sleep mode. LESENSE can be thought of as a control unit that can operate in deep sleep and utilize other on-chip peripherals like the analog comparators or digital to analog converter to measure and evaluate analog events. Up to 16 individual inputs can measure inductive, capacitive or resistive types of sensors. The programmable Statemachine can then decode and evaluate several sensors without waking up the CPU. It can also take advantage of the peripheral reflex system to relay signals to other on-chip peripherals, like UARTs or timers. Now we will have a look at the different peripherals that LESENSE can use in deep sleep mode. The most central peripherals for LESENSE includes the analog comparators, the digital to analog converter, and the low frequency oscillator. In addition, LESENSE can use both DMA, peripheral reflex system, pulse counter, or the auxiliary high frequency oscillator from deep sleep for more advanced tasks. The first example on how it actually works is capacitive sense. The EFM32 analog comparators has a special capacitive sense mode which works by setting up an RC relaxation oscillator on the touch pads. LESENSE can autonomously measure and evaluate the change in frequency and issue an interrupt only when the change crosses a predefined threshold. When a human finger comes close to the touchpad, the capacitive value changes, which in turn changes the oscillation frequency. An interrupt can then be issued. Typical current consumption is less than 2 microamps while monitoring a couple of touch buttons. Now we will see a live demonstration of capacitive touch using LESENSE. First, I will open the EnergyAware profiler from Simplicity Studio. Then I will go to the demo mode and start the touch slider example. First, I will measure the average current consumption in the profiler window by placing 2 markers, like this. And then the average consumption will show up as a number at the bottom of the profiler. It is around 2 microamps. If I press play again and try to touch the slider on the starter kit, we should see that the MCU wakes up, and you can also try to slide your finger across the pads for the text to scroll on the LCD. After the finger is removed, you can see that the microcontroller goes directly down to deep sleep again. In the next example, we look at resistive sensors, or any sensor with an analog voltage output. The power to the sensor itself is duty cycled by a pin on the EFM32 to save power. The analog comparator is used to sample the sensor value, returning 0 or 1 depending on the selected threshold voltage. Consider the case where the output of the sensor is an analog value that stabilizes after a power-up delay. LESENSE can autonomously turn on the power, wait an appropriate amount of time, and then sample the sensor, as we can see here. The state of the sensor can either cause an interrupt directly, or it can be further processed in the LESENSE state machine, which we will look at later. The true or false value from the comparator can also be passed on to other peripherals through the peripheral reflex system. Typical consumption for these kind of applications is less than 1.5 microamps. Now we will see a live demonstration of LESENSE sensing a resistive type of sensor. We will open the LESENSE demo in the EnergyAware profiler. First, I will try to measure the average current consumption by placing 2 markers like this, and then the average consumption is shown down here. It is around 2 microamps. If a finger covers the light sensor, you can see that the microcontroller wakes up, displays something on the LCD, and then goes to sleep again after a couple of seconds. In this example, sensing the proximity of metal is considered. The sensor consists of an inductor and a capacitor in parallel, also called a tank circuit. The tank circuit is operated by keeping one side of the sensor at a fixed voltage relative to ground. The digital to analog converter is used to keep the fixed side at a suitable voltage between ground and VDD. The other side of the tank circuit is first pulled low to excite the system. Current flowing in the inductor sets up a magnetic field which stores energy in the tank circuit. After current is flowing through the inductor, the comparator input is tri-stated. The current in the inductor must now flow into the capacitor, transferring the energy to the capacitor, which in turn, when charged up, passes the energy back into the inductor. The magnetic field around the coil keeps changing. The system is allowed to oscillate freely like this, and you can see the voltage at the comparator input in the figure on the right. LESENSE can autonomously excite the sensor and then measure how long the oscillations keep going. Here we see oscillations at the comparator input without metal nearby. If metal is near the coil, eddy currents induced in the metal will drain energy from the oscillating system faster than if no metal is near the coil. This causes the oscillations to die out faster, as we can see in the second waveform. By automatically counting and comparing the number of comparator trigger pulses against the threshold value, LESENSE can issue events based on the presence or absence of metal, typically with consumption of less than 2 microamps. Now we will see a live demonstration of the metal sensor using LESENSE. We will open the LESENSE example in the EnergyAware profiler. First, I will measure the average consumption by placing 2 markers like this, and the average consumption is around 2 microamps. When metal approaches the coil in the bottom right corner of the starter kit, you can see that the MCU wakes up and displays something on the LCD. Now we will take a look at a specific timing sequence within one LESENSE scan event. LESENSE can automatically scan up to 16 enabled sensor channels at a fixed scan frequency. Here only 2 channels are used. Consider the same metal sensing example as in the last slide. Within one channel scan event, there are 3 individual timings happening. The first is enabling the analog comparator and the digital to analog converter, as these are duty cycled by LESENSE to save energy between measurements when they are not used. These peripherals will typically stay active during the whole measurement. The second step is the excitation of the sensor. For the metal sensor, the excitation pin is the same as the sensing pin. The pin is pulled low for a short time at the start of the measurements. It is then released and put in a high impedance state. The pin voltage is passed on to the comparator for the rest of the measurement cycle. The oscillations in the tank circuit start right after the pin is released. The last step is to gate the analog comparator output to a counter in the LESENSE module. In the figure, 6 pulses are counted before the oscillation amplitude is below the threshold. At the end of the sample window, the counter value is compared against a configurable threshold value. It is this comparison result that is the final output of the whole measurement cycle. This true or false value can be used to trigger an interrupt, trigger events in the state machine, or it can be passed to the peripheral reflex system after the scan cycle is complete. By combining several LESENSE channels, more advanced autonomous functionality is possible. Here we see a rotating wheel in a water meter, partly covered with metal. LESENSE does the inductive metal measurements at a high sample rate. The measurements end up with a true or false value, depending on if metal is near the 2 sensor coils. The true or false value is then sent out on the peripheral reflex system. In the other end of the PRS channels, the EFM32 pulse counter receives the signal. The pulse counter can interpret the 2 Boolean values as a quadrature encoder signal and count rotations. An interrupt is issued only when a certain number of rotations has been counted. Everything that happens until the interrupt is issued happens in deep sleep with only microamps of current drawn by the EFM32. Another example of the possibilities of autonomous operation with LESENSE is capacitive touch gesture detection. This example demonstrates how the internal state machine in LESENSE, or the decoder as it is called in the reference manual, works. Here we see a capacitive touch slider connected to LESENSE. The LESENSE decoder interprets the capacitive scan results and transition between states in deep sleep mode without any intervention from the CPU. When a finger approaches and passes the pads, the state machine keeps track of the order the pads are activated in. The state machine can issue an interrupt when the finger has passed all the pads in the configured order. Up to 16 states allows for more advanced functionality than demonstrated here. The state machine can also pass event signals as peripheral reflex pulses instead of issuing interrupts, allowing even more functionality in deep sleep mode. What would happen if the slide is not performed correctly? Here we see the same wake on slide example, but now with the demonstration of operation when the slide is aborted before finished. We can see that the state machine just transitions back to the first state and no interrupt is issued when the finger is removed too early. The system can stay in deep sleep mode the whole time, only consuming a couple of microamps. How does this decoder or state machine actually work? Consider a scan period with 4 sensor channels enabled. At the end of every scan cycle, a decode step is added, which is the state machine transition step. Each channel scanned results in a true or false bit, which is stored and passed as a 4-bit value to the decode step at the end of a cycle. The state machine step consists of a decision block which determines if the state machine should go to one of 2 possible next states. The decision is based on what the previous state was and the 4-bit input value. While transitioning to a new state, the decision block can also issue PRS signals or interrupts based on which next state is selected. This decode and transition step happens at the end of each scan cycle. Here we see that the previous scan cycle has the same decode block which sent us to the current state. The same is true if we look into the future. The next scan cycle also ends with a decode step, which transitions the state machine even one step further, based on what state was entered in the current decision step. A summary of the main decoder features are: up to 16 states can be configured. It can use up to 4 input bits from either the channel scan results or the peripheral reflex system. There are 2 configurable next states per transition. 3 output action signals on state transitions. It can also issue an interrupt on state transition, and there is 1 transition per scan sequence. Thank you for watching this Lizard Labs demonstration of the low energy sensor interface. For more information, please go to energymicro.com.